Hi, we're doing Newton's second law. Here's what I'm going to do in this video. I'm just going to do an example of adding two forces just for the practice before we do Newton's second law. And I'm going to do two ways of looking at Newton's second law. I'm going to use it for finding an acceleration, and then I'm going to use the case of equilibrium. So first, just practicing adding forces. Suppose I have some sort of anchor like this, just a connector, and I have two forces acting on it. So a cable like this and a cable like this. This one has a 65 Newton force, and this one a 75 Newton force. This is at 12 degrees, and this one's at 22 degrees. And I just want to know the net force on this connector. This is just a kind of an eye bolt that's bolted into the wall. For engineering reasons, I need to know the net force on that. So I just have to add up the x components and add the y components. So for this one has an x component and a y component. This y component is 65 sine 12. Its x component is 65 cosine 12. This one has an x component and a y component as well. So let's look at those. The sum of the fx says our fx will be 65 cosine 12. This one is 75 cosine 22. And I've added those. That gives you 133 newtons. Our Fy, or sum of the Fy's. So I've got a 65 sine 12 up. And then this one is down. So I've got a minus 75 sine 22. And that is minus 14.6 newtons. So those are my components, Fx and Fy, of the total force. So if I want to know the total force, F, it's Fx squared plus Fy squared square root. So it's 133 squared plus minus 14.6 squared square root. That just gives you 134 newtons, it turns out. If I want to know the angle of the total force, theta is inverse tangent of Fy magnitude over Fx magnitude. That's inverse tangent of 14.6 over 133. And that gives you 6.26 degrees. Notice I took the absolute value in getting the angle, but the minus sign does matter. That says the angle is down like that, because that's where you have a negative y part but a positive x part. So that says this is below the plus x-axis. Or there's an engineering notation for that that looks like that. So that's just practicing adding forces to just kind of get our brains started before F equals ma. So F equals ma. One way we use Newton's second law is when we want to know F or A. That makes sense. So one case, for an example, might be if you have a car heading down the road and you need to stop that car. So here's an example. You've got a car that's moving with a velocity of 30 meters per second, and it needs to come to a stop over a distance of 90 meters. But now, rather than just wanting to know the acceleration like in the previous chapter, we want to know what force does it take to do that. So we know F equals ma. So we need to know the mass and the acceleration. So I chose this to be a 1,000 kilogram car. That's about the mass of a small car. So we need, if we know the mass, we need the acceleration, but now we can find the force. To get the acceleration, v squared is v naught squared plus 2ax. X is 90 meters. V final is 0 because we're bringing the car to a stop. So A is minus v naught squared over 2x. I plugged all those in and got, let's see, minus 5 meters per second squared. So now F is MA is 1,000 meters per, no, not 1,000 meters, it's 1,000 kilograms times minus 5 meters per second squared. This says the force we need is minus 5,000 newtons. That's how much force it takes to stop the car. See how we've learned more than the previous chapter where we knew acceleration, we knew how rapidly it needed to stop. Now we know how much force it takes to stop it, which could tell us something about the surface or the tires. Okay, so there's one case of F equals MA. You want to know either F or A. There's actually a surprisingly common case where you use F equals MA, and that's the case of equilibrium. An object is in equilibrium if the acceleration is 0. So if A is 0, AX is 0, AY is 0, that means F is 0, F net is 0. So the sum of the Fx equals 0 and the sum of the Fy equals 0. That's called the first condition for equilibrium. Yes, there's a second condition, we'll learn it later in the semester. It has to do with rotation. This has to do with translation, where the object is moving or not. The second condition has to do with rotation. So if the object's in equilibrium, the sum of the forces on it have to be 0. So I've got a couple of examples of that. Suppose we have an object sitting on a cable. Suppose it's like a tightrope walker here with a weight mg. This is, I chose pounds here to make it easy to think about. So it has a weight of 20 pounds. And this cable then has a tension in each side, T. Tension is a force in a flexible connector. So we often call forces in flexible connectors tension. So this could be in a rope, in a chain, in a cable. When it's that type of force, we call it a tension, T. So we've got a cable. If you stood on a cable like that, you'd be pulling this way and you'd be pulling that way. If these angles are equal, then those tensions are equal. In my example, this angle is 5 degrees and this angle is 5 degrees. So to be in equilibrium, the sum of the Fx equals 0. So that would say Tx, that would be Tx would just be T cosine 5. Over here, I would have T cosine 5 as well. So I would just have T cosine 5 minus T cosine 5 is 0. And that really didn't tell me anything. That just says the T's are equal because those angles are equal. In the y direction, I've got a Ty here. I've got a Ty here, where that Ty is T sine 5 plus T sine 5 minus W equals 0. This says 2T sine 5 is W. I know I'm going kind of fast, but I'm assuming if you need to stop the video. So T is W over 2 sine 5. W is 22 pounds over 2 sine 5, gives you 126 pounds. So when you've got slight angles like that, to hold a little force takes an actual big force in a cable. That's just an aside, but it came out in this example. So there's our one example of equilibrium. I'm going to do one more, then we'll call it a day, and you can practice this in your homework. So here's another case of an object in equilibrium. Got an object, just a crate, it's just hanging here. Got a cable here, a cable here. This is a 22-degree angle. This is a 35-degree angle. And it's got a weight mg. It's a 12-kilogram crate. Since and it's hanging by cables, so these are tensions. I've got a tension T1 here This is a tension T2. These tensions are not equal because these angles are not equal. So if this angle is 22, this one is 22. If this angle is 35, this one is 35. Your geometry teacher taught you that. Those are alternate interior angles. So in the x direction, actually I did y first in my notes. So in the y direction, the sum of the fy is 0. So I've got T2 sine 22. That's T2y. T1y is plus T1 sine 35 minus mg equals 0. In the x direction, the sum of the fx equals 0. I've got an fx here, that's T2 cosine 22. I've got an fx here that points the other way, so minus T1 cosine 35 is 0. This tells me that T2 is T1 cosine 35 over cosine 22. I can now plug all of this in for T2. And I've got T1 cosine 35 over cosine 22. That's T2 times sine 22 plus T1 sine 35 equals mg. That looks worse than it is. Remember, these cosines and sines are just numbers. I can factor out a T1 and get T1 times cosine 35 sine 22 over cosine 22 plus sine 35 equals mg. Checking my notes to make sure I did that right. Yeah. So T1 is mg, where m is 12 kilograms, g is 9.8. Divided by all of that. If you do that, this implies that T1 is 130 newtons. So you can do that to make sure that you know how. Once you know T1, you can plug it back in here and get T2. T2 is then 115 newtons. So now we know the forces in these cables for this to hang in equilibrium. So as usual, you can practice this in your homework. Hope you're enjoying your weekend, or maybe it's already over, and I will see you soon.